All right, so we're going to continue our talk with resonance and standing waves, but we're going to do it inside of air columns. So you can have two types of air column. A closed air column, and when I say closed air column, I only mean one end of the air column is closed, right? In this case, the bottom end. An open air column just means it's opened at both ends. Okay, that's very important. It's kind of useless to have a musical instrument that's closed at both ends. So closed is only closed at one end, open is opened at both ends. Now in order to get resonance, you need to have a standing wave in there. Now a standing wave, remember, has nodes and antinodes. And what's going to happen is at your closed end, that will act like a fixed end. So you're going to get a node right here. At your open end, that acts like a free end, so you're going to get an antinode right there. So notice with your closed air column, you have a node and then an antinode. With your open air column, you have two antinodes. Now these two pictures that I've shown are both at the fundamental frequency. So what do I mean by fundamental frequency? I mean you could not draw this standing wave any longer, because it's going from one antinode to the next antinode in our open air column. In our closed one, we're going from one node to the next antinode. Now what you can do, and I'll draw this for you. For a closed air column, draw a closed air column. Now the first one goes from node to antinode. I can draw it a little bit shorter, well the wavelength shorter, if I go from node, not to the first antinode, but to the second antinode, like this. That would be your next frequency that would produce resonance. And you could draw the next one too. Okay, so you go not to this antinode, not to that one, but to that one, like this. And that would be the next frequency that would produce resonance. Okay? Our first fundamental frequency that produces resonance right here, we call that our first harmonic. This would be our second harmonic, and this would be our third harmonic. Now, notice the lengths. If we're to count wavelengths, this one just goes from node to antinode. So that's 1/4 of a wavelength. This one, we go half and then another quarter. So the length of that air column is equal to 3/4 of a wavelength. And the next one, well, from here is 1/4, a half, 3/4, 1, and 1 1/4, or 5/4. So the length is 5/4 wavelength. You might start to notice a pattern. The next one will be 7/4, and then 9/4, 11/4, 13/4, and so on.
Why are they all in proper fractions?
I prefer improper fractions. Okay, and it also helps to show the pattern. The pattern would be harder to see. Over 4? They're all over 4.
Yeah, no, why?
Because that's where we start with, right?
Oh,
From node to antinode, that is 1/4 wavelength.
oh,
Okay? Now you can probably see a pattern, right? 1/4, 3/4, 5/4. So if we're to write this as an equation, now I have the equation here for you, for a closed air column, the equation is 2n minus 1 lambda over 4. So what's n then? N is the harmonic number. So I told you this is the first harmonic. That's n equals 1. This example is the second harmonic. So that's n equals 2. And this example is our third harmonic. So that's n equals 3. Try one of those in the equation, like n equals 2. If we take this equation and solve for L2, you would get 2 times n, which is 2, our second harmonic, minus 1 lambda over 4. And this is 4 minus 1, which is 3. So 3/4 lambda. So that gives you the length of the wave, the wavelength, inside of that closed air column. Glasses are fogging up. Now I could continue to draw the open air column as well. Now the shortest possible resonance you can draw would be from one antinode to the next antinode. So if I were to draw the next one, we can go from one antinode, not to this one, but to the next one, to make it one little bit longer. So what would that be? So the length of our air column would then be, well, from here to here is half, to here is 1. So 2 over 2, or just one wavelength. If I were to make those wavelengths even shorter, we wouldn't go to this one or this one, but we would go to that one, like so. In this case, we have half a wavelength, 1 wavelength, and then 1.5 wavelengths, which would be 3/2 wavelengths. So you can start to see a pattern here. 1/2, 2/2, right? If you want to think of it as 2/2. 3/2. Next one would be 4/2, 5/2, 6/2, 7/2, and so on. So to figure out the wavelength for an open air column, we say the length of the air column for whatever harmonic equals n lambda over 2. So in this case, if you look at this one, which is our third harmonic, or n equals 3, third harmonic, you would get the equation L3 equals n lambda, where n is 3, lambda over 2, which is exactly what we drew. Okay, now you can see I have other pitches on my handout which are much better than the ones I've drawn down here. So this one here is for your, should probably write it above. This one's for your closed air column, and this one's for your open air column. So here's our fundamental or first harmonic for closed and open. Here's our second harmonic. Now our second harmonic we also call one more than the fundamental, which we call the first overtone. Third harmonic would be the second overtone. Fourth harmonic would be the third overtone, and so on. Okay, next thing I want to talk about is beats. So I have a little demonstration here, which I used to show resonance before. Okay, but this time I've slightly altered the frequency of this one. So these two are no longer identical. Tell me what you hear when I ring them. more time. Okay, so can you hear the wow, 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 wow? So those are beats. So what happens here, and I have a diagram because I can't draw. These two frequencies here look almost identical, but they're not. They're slightly off. And because they're slightly off, you don't get a perfect standing wave. What happens is, you do get some kind of a standing wave, but notice that the amplitude decreases and increases overall over time. And so that's what gives you the wow, 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 wow noise. Now what I'm going to do is I'm going to make those frequencies a little further apart. So tell me what you hear. So now the beats are a lot faster, isn't it? And so on. Now I'm going to make them closer together so the frequencies are almost the same. And tell me what you hear. So in that case, wow, wow, wow. So there's less beats. Or you can say the beat frequency is smaller. Until eventually, if you can get them to be identical, move this one up. There. No more beats. So this is actually how you tune an instrument. If you take a tuning fork with a known frequency and you want to match your instrument to that frequency, you tune your instrument until you can't hear the beats anymore. You want the beats to get further and further spread apart, or to have a smaller and smaller frequency until you can't hear the beats anymore. Now it's important you don't want the frequency to get larger and larger, because the human ear can only hear beat frequency up to a certain amount. Can't remember the exact amount, but somewhere only between 7 and 10 hertz. Above that, it's too fast that we can't distinguish them. But at that point, the notes should also sound different. All right? Okay. Now, because the beat frequency is smaller, the closer those frequencies are together, there is a pattern here. And we can say the beat frequency is the absolute value of the difference between those two frequencies. Which would mean if one frequency was 100 hertz and the other was 99 hertz, your beat frequency would be 1 hertz. You would hear one beat every second. If they're further apart, like 100 and 98, your beat frequency would be 2 hertz. So you would hear 2 beats every second. All right, let's try some problems here. I'm fogging up again. So in our first problem, and this is on the back of your page, we have a tuning fork with a frequency of 256 hertz is held above a closed air column while the column is gradually increased in length. At what lengths for this air column would the first 4 resonant points be found, given the speed of sound? Okay, if that's the speed of sound, now it's a closed air column, so we know the formula. Ln is 2n minus 1 all over 4 times lambda. Which means the first one, or I don't know, let's just pick a random one, the third one then, the third resonance length, or the third harmonic then, would be 2 times 3, so 2 times 3, minus 1, lambda over 4, which would be equal to, well, 6 minus 1, which is 5 over 4 lambda. Now, they don't tell us what lambda is. They tell us the frequency, and they tell us the speed. So in this case, we can use the universal wave equation, speed equals frequency times lambda, to figure out what lambda would be. So lambda would be speed over frequency. So I can put that straight into here. So the third resonant length would then be 5/4. Lambda is speed over frequency, which is 330 meters per second, all divided by the frequency, which is 256 hertz, which is 1.6 meters. Now you can do the same thing, and you can solve for L1, L2, and L4 to figure out the 4 lengths. But what does this actually mean? So I'm going to show you, because right over here I have an air column. Right? Over here it's open, and then there's water at the end. The level of the water would simulate where the fixed end is going to be. So the length of our air column goes from where the water is up to where it's open. Now this is a tuning fork, 128 hertz. So let's figure out where the first resonant length, or how long that air column needs to be for the first resonant length to occur. And then we'll listen to it to see what it is we're actually hearing. So let's go to the side. We're going to do this exact same question again. Because for a closed air column, the length is, again, 2n minus 1 over 4 lambda. But for the first one, that just equals lambda over 4, or 1/4 lambda. Now again, we don't know the speed of sound. We don't know the speed of sound, but we've learned how to calculate it. Remember, the speed of sound is 331.6 plus 0.606 times the temperature. So what I can do is I can say, assume we're in room temperature here. So let's say 20 degrees. So the speed of sound in this room will be about 331.6 plus 0.606 times 20 degrees Celsius. And let's just see what that'll give us. About 343.8. So I'm just going to round to 344. 344 meters per second. That's the speed of sound in this room. Okay, now we know lambda is speed over frequency. So I'm just going to write that as v over frequency, and I still have that 4 there. So our first resonant length will occur at 344 meters per second divided by 4 times the frequency of this tuning fork, which is 128 hertz. And we'll get our first resonant length to be 0.67 meters, or 67 centimeters. So what I'm going to do here, I'm going to adjust the water level to 67 centimeters, which would be all the way down to here. Coming down, 65, 66, Went a little bit below 67. Okay. Now let's try and hear what this sounds like. Listen again. I'm going to raise the water level a bit high, and I'm going to have a drop, and as it's dropping, we'll listen. And you can tell me when it hits 67. Okay, one more time. All right, so this is 256 hertz. At 33.5 centimeters. And I'll rise it. Drop it. Okay. Now when I rise and drop it, if you're not hitting the resonance frequency, you're just getting something weird, like some weird pattern forming that's not a standing wave pattern, and so you're not going to get an increase in your amplitude. Remember, standing wave transfers energy at the right frequency to increase its amplitude. Okay? So our second question says, a wave that vibrates with a fundamental frequency of 256 hertz in a string is stretched between 2 points 2.4 meters apart. What is the wavelength for this first harmonic? Well, if you have a string, what you're doing is you're creating a node at both ends. So your standing wave would look like this, just like the demo I showed you before on, well, the string. So if you have a node at both ends, this is the smallest possible frequency and the largest wavelength you can have. And that is, the length of that is exactly 1/2 wavelength. It follows the same pattern as an open air column. And you can even use the same formula as well. Well, if the length is 1/2 times the wavelength, and we know the length of the string, that's 2.4 meters. Well, 2.4 meters, if we're solving for lambda, times 2 equals lambda. So lambda is then 4.8 meters. So our wavelength is 4.8 meters. Then it says, what is the frequency of the third harmonic? Okay. Well, our third harmonic would look like this. So there's our first, second, and third. Something like that. Okay, so the length would be 3/2 wavelength. Now the interesting thing is, for harmonics, here's a good relationship. So the frequency of the nth harmonic is simply n times the fundamental frequency. So the frequency in our case for the third harmonic is just 3 times the fundamental frequency, or 3 times 256 hertz, which is 768. And if you wanted to figure out the wavelength, well, the length of the string hasn't changed. It doesn't ask for wavelength, but why not? The length of the string hasn't changed, so we can just say that lambda is 2 over 3, just rearranging, 2 over 3 times the length, which is 2.4 meters. So 2.4, 1.6. So notice that as frequency increases, wavelength decreases. And what you'll notice in the lab you're going to do later today is that the speed of the wave won't change. Because remember, the speed of the wave is frequency times wavelength. As frequency increases, wavelength decreases, and it does so at just the right amount. So our third example is on beats. So let's say we have a frequency of 550 hertz. This is a known frequency. And then we have some unknown sound. And when played together, we produce a beat frequency of 5 hertz. Now our goal is to figure out what that unknown frequency is. But our beat frequency, all right, FB, equals the difference between these two frequencies. So if our beat frequency is 5 hertz, and our known frequency is 550 hertz, that gives us two possibilities. F2 can be 5 more hertz than that at 555, or it can be at 5 less hertz than that at 545. Each would give you the same beat frequency. So then we get to part B. If we have a different sound played with this unknown sound, where this is 544 hertz, and you get a beat frequency of only 1 hertz, well, this gives you two possibilities as well. Either one more than that or one less than that. So it's either going to be one more than that at 545 or one less than that at 543. 543. Since the frequencies are identical, we look for the two that match. And that's the frequency of our unknown sound.